Well, my video stopped recording, so here I am again. So the reason you have this FET input op amp here as a follower is the FET input of this op amp has an absolutely tiny bias current and an absolutely gigantic input resistance. So the charge will stay on the capacitor for a long time when the switch is open. So that's good. And then you come over here and you can look at it with your scope probe. If you put the scope probe directly over here, the finite resistance of the scope probe would drain the charge off of this capacitor quickly. So this is the trick. Use a FET input op amp here to hold the charge, keep the charge from draining off of this capacitor. And the 411 op amp has the same pinout as the 741, but being a FET input, it has a very low bias current and a gigantic input resistance. So we're going to have negative power to pin 4, positive power to pin 7, and then we'll have feedback from the output pin 6 back to the inverting input pin 2, and then our input will be on the non-inverting input pin 3, and then pins 1, 5, and 8 will be no connects. Now I built this entirely using +5 and -5 from the analog discovery board, and that seems just fine. So you don't need plus and minus 15 or even plus and minus 9 from the batteries. The analog discovery board plus and minus 5 is just fine. So the DG403 has those 4 power connections that we saw in the earlier videos. You have pins 11, 12, 13, 14, or +15, +5 ground, and -15, where I replaced +15 with +5, I replaced -15 with -5. So it's basically +5, +5 ground, -5. I keep them separate just in case I want to use the 9-volt batteries at some point in the future. And this being a CMOS input, unused, I keep it grounded. This is the switch back and forth input we're using, and this is the connection we're either making or breaking with the analog switch. Okay, so at pin 16, that's basically the source of this first switch channel. I have my waveform source in yellow, and I have my scope probe to watch the input waveform source in orange. Next to that, pin 15 is the switch on and off input. Tom recommended a handheld switch for that, but I'm using yellow with a white stripe, which is the second waveform generator output. And I'll show you what I'm doing with that in a moment. Then pin 1 is the drain for that FET switch channel. So there's a 100 picofarad capacitor to ground, and then this yellow wire is taking the output of the sample and hold and running it to the non-inverting input of this 411 op amp. That's pin 3. And there's the feedback connection from pin 6 back to pin 2. That's the output back to the inverting input. Here's the negative power, which is going to what would be, well, it's -5, nominally -15, but it's -5. That's from pin 4. And then pin 7 is the positive power supply for the op amp, which is going up to what would be +15 or +9, but in fact I just have it jumpered between up over to the +5 for this setup, and it seems to work fine. So let's go to, okay, so in power supplies I'm using both +5 and -5. Waveform generator, now I'm using 2 channels of the waveform generator. So this sine wave is my signal source, so it's kind of like you imagine this to be the signal that you're trying to hold on to and digitize. So it's the signal is being sampled periodically. And then this is a 100 hertz sine wave. And I made it 0 offset, 4 volts amplitude. And then down here I have a 1.1. I made it 1.1 just to make it not quite evenly line up. Anyway, this is a 1.1 kilohertz square wave. Could be 1 kilohertz, could be 0.9 kilohertz, that could be anything you like. Anyway, it's a square wave, and this is important. So 2.5 volt amplitude, 2.5 volt offset, so it goes back and forth between 0 and 5 volts. Because this is a logic input, it's a CMOS logic input, so you don't want this to go above 5 volts or below 0. So it's going back and forth between 0 and 5 volts. Now we look with the scope, and we see, so the yellow is the input waveform, and then the blue is what's coming out of the LF411 op amp, and you see that here the switch is closed, so the sample and hold is following the input signal. Then the switch is open, so the output just stays where it is, and now it's closed, it tracks, and then it's open, it just stays put. Actually, come to think of it, I can go back and change the symmetry on this waveform. Let's see, if I go 10% symmetry. Yeah, so now it's only tracking 5% of the time. Let's see what that looks like. Yeah, I think that's what I want. See, so here it says, okay, track the signal, now just hold that. Track the signal, 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 hold that, blah, 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 blah. Track the signal, hold that. Track the signal, hold that. Track the signal, hold that. So that's pretty cool. So then you can see it's as if maybe it takes you a while to record each new sample that comes in. So you say, okay, let's grab a sample, hold on to it for long enough to write it down. Grab a sample, hold on to it for long enough to write it down. Grab a sample, hold on to it for long enough to write it down, and so on. That's essentially the purpose of a sample and hold. If you have a slow digitization process, you want to hold the sample steady while you take the time to digitize it, turn it into digital form. I guess we could also look, instead of looking at the input waveform, we could look at the switch back and forth waveform. Well, that's kind of hard to see, but you can see it's basically just that square wave with a funny period. It's not really, I mean, it's either 0 or 5 volts. It's most of the time it's 0, once in a while it's 5 volts. It's a little hard to look at. That's better. Okay, so the sample and hold seems to work, and it works without any funny power supplies.